Good morning, friends. Last we discussed about the velocity and acceleration for a simple harmonic oscillator. That means a particle performing a simple harmonic motion. And we also discussed its cases. That means at which position the velocity and acceleration maximum, and at which position both, that means the velocity and acceleration are minimum. Velocity is maximum at mean position, while at the extreme point velocity is minimum, that means the zero. Now opposite to that, acceleration is minimum at mean position, and at extreme point acceleration is maximum, because at extreme point the direction of motion is changed. Therefore the acceleration is maximum. Okay. Now today we are going to discuss about the kinetic energy, potential energy and total energy, that means the mechanical energy of a particle performing simple harmonic motion. For that purpose we know that the kinetic energy half mv square, right? M is the mass of a particle which performs the simple harmonic motion. Now here we have to substitute the equation or the value of velocity of a particle. For that purpose, we start our discussion from the displacement of a simple harmonic oscillator or a particle performing a simple harmonic motion, and we take the derivative or the differentiation of the displacement with respect to time, that gives the velocity. Thus we obtain the equation of kinetic energy. Now, what is the potential energy? For that purpose, we know that the potential energy is that the work done against the force. Actually, for the conservative force, we can define the potential energy. The work done against the conservative force acting on a particle is stored in this particle in form of potential energy. Therefore, from the concept of the work done, we are using the concept of the work done to derive the equation of potential energy. Now the mechanical energy, that means the total energy. Total energy is the sum of kinetic energy plus potential energy, right? Okay. And then we are trying to do the graph of kinetic energy, potential energy and mechanical energy versus displacement of a simple harmonic oscillator. First, we are going to discuss about the kinetic energy. For that purpose, the displacement of a particle performing a simple harmonic motion at time t is given by the equation xt is equal to a cos omega t plus r. That is the equation 1. A is amplitude and omega is the angular frequency. Now, differentiating equation 1 with respect to time. With respect to time t. Therefore, velocity at time t is vt is equal to dxt upon dt is equal to, substitute the value of xt. Therefore, d by dt, here a cos omega t plus r. A is constant taken out and remaining is cos omega t plus phi. So is equal to A. Here, derivative of cos omega t plus phi is minus sin omega t plus phi. Therefore, minus sin omega t plus phi, and derivative of this bracket is omega. Therefore, minus a omega sin omega t plus phi. That is the velocity v. Equation number 2. Now, kinetic energy of a particle is K is equal to half m v square. Here we have this form K into K kinetic energy, half m v square. Substitute equation 2. Therefore, kinetic energy is equal to half m as it is. Now, the square of velocity, therefore minus a omega sin omega t plus phi whole square. Therefore, half and square of this, therefore negative becomes the positive. Half m is square omega square sin omega t plus phi sin square. Now, we know that the m into omega square is equal to k, is equal to half k square. Half k square sin square omega t plus phi. That is the equation of the kinetic energy. Equation number 3. Again, we derive how we obtain the kinetic energy. We know that the displacement of a particle performing a simple harmonic motion at any instant time t is given by the equation xt is equal to a cos omega t plus phi. Now we know that in chapter 3 and 4 we obtain the equation of velocity. Derivative of displacement with respect to time, that gives the velocity. Right? Okay. Therefore, differentiating equation 1 with respect to time t, we obtain the velocity of time t is vt is equal to dxt upon dt is equal to d by dt into bracket a cos omega t plus phi. A is common because there is constant amplitude a into d by dt of cos omega t plus phi. Now, derivative of cos omega t plus phi minus sin omega t plus phi, and derivative of this bracket omega t plus phi is omega. Therefore, velocity at time t vt is equal to minus a omega sin omega t plus phi. Now, kinetic energy of a particle for the simple harmonic oscillator is kinetic energy is equal to half v square. Substitute the value of v. Therefore, kinetic energy is equal to half m into bracket minus a omega sin omega t whole square is equal to half m a square omega square sin square omega t plus phi. But we know that wave vector k is equal to m omega square. M omega square. Therefore, instead of the m omega square, we substitute the k. Half k square sin square omega t plus phi. Clear this? Okay. After that, we are going to discuss about the potential energy. Now, for the potential energy, we are using the concept of the work done. For that purpose, doing the simple harmonic motion for displacement x, for the position x, the destroying force acting on a particle or the simple harmonic oscillator is F is equal to minus kx. In simple harmonic motion, the strain force act on a particle at x distance from mean position is fx is equal to minus kx. Minus kx. K is the force constant. K is force constant. Now, after that, the work done by strain force for small displacement. Now, work done by the strain force for small displacement dx is W is equal to force into displacement is equal to minus kx into dx. Minus kx into dx. Thus, total work done from x is equal to 0 to x displacement is W is equal to integration of dW is equal to integration x is equal to 0 to x minus kx dx. So here minus k is common, taken out, 0 to x, x into dx. Therefore, is equal to minus k, here x square by 2, 0 to x. Because we know that from this equation, integration x raised to n. We are using this concept, integration x raised to n into dx is equal to x raised to n plus 1 upon n plus 1. Here only x power is 1. Therefore x raised to 1 dx. So x raised to 1 plus 1 upon 1 plus 1. Therefore x square by 2. So is equal to minus half kx square. That is the total work done. That is the equation number 5. Again, friends, how we obtain the equation of the kinetic potential energy. For that purpose, in simple harmonic motion, the strain force acting on a particle at x distance from the mean position is Fx is equal to minus Kx. Here K is the proportionality constant or the force constant. Now, work done by strain force for small displacement dx is dW is equal to F into dx is equal to minus Kx into dx. Thus, total work done from x is equal to 0 to x displacement. That means from mean position to the x displacement is we obtain by taking the addition of this type of the work done for the small displacement. Here all the displacement are continuously distributed. Therefore, instead of the addition, we directly consider the integration. Therefore, W is equal to integration dW is equal to initial position x is equal to 0 to final position x minus kx into dx. So minus k is taken out, that is constant. Integration from 0 to x dx. Actually the power of the x is 1. According to this equation, integration x raised to n dx. So its answer is x raised to n plus 1 upon n plus 1. Value of this integration is x raised to n plus 1 upon n plus 1. Now, according to this, here the power of x is 1. Therefore, x raised to 1 plus 1 upon 1 plus 1, therefore x square by 2. Now we substitute the x as upper value, x square by 2. And then 0, x as 0, 0 square by 2, that means the 0. So I directly add down minus half kx square. That is equation number 5. Here is now thus we get the equation of the work done by the restoring force for the displacement x from the mean position. Now, the work done against the restoring force is stored in a particle in form of potential energy. Now, the work done against the restoring force is stored in form of potential energy in a particle. Therefore, potential energy is equal to minus of work done. Potential energy is denoted by U is equal to minus, and from equation 5, minus half kx square. Half kx square. So it's equal to half kx square. But k is equal to m omega square and x is equal to a cos omega t plus phi. Therefore, half m omega square and x is equal to this a cos omega t plus phi whole square is equal to half m omega square a square cos square omega t plus phi this. So is equal to half k square cos square omega t plus phi. That is the equation of potential energy at x distance from the mean position. So thus we obtain the equation of the kinetic energy and potential energy. Kinetic energy and potential energy are the periodic function of time. Kinetic energy and potential energy are periodic function of time. Kinetic energy is maximum at mean position. Maximum at mean position and 0. That means the minimum at extent point x is equal to plus or minus a. Now, what about the potential energy? The potential energy is maximum at extreme point x is equal to plus or minus a and 0 or minimum at mean position. The periodic time of both periodic time of kinetic energy and potential energy is T by 2, because within the periodic time of oscillation, twice time becomes the maximum and twice time becomes the zero. Both the kinetic and potential energy, therefore the periodic time of kinetic energy and potential energy is now T by 2. So after the equation of the work done by the storing force, now the kinetic energy is the work done against the storing force, is stored in a particle in form of potential energy. Therefore, potential energy is equal to minus W. Therefore, U is equal to minus half kx squared. Therefore, half kx squared. But k is equal to m omega squared and x is equal to a cos omega t plus phi. Therefore, half m omega squared into bracket a cos omega t plus phi whole square. Therefore, half m omega square cos square omega t. Now again we substitute the m omega square is equal to k, because next we are directly using the equation of kinetic energy this form to obtain the total energy. Therefore, U is equal to half k square cos square omega t plus. Kinetic energy and potential energy are periodic function of time. So there is a continuously changes with time t. Kinetic energy is maximum at mean position and 0, that means the minimum at extreme point x is equal to plus or minus 8. Mean position is x is equal to 0. Now, similarly, potential energy is maximum at extreme point x is equal to plus or minus 8 and 0 and the minimum at mean position x is equal to 0. Now, kinetic energy and potential energy both are the periodic function and periodic time is T by 2. Now, total energy, that means the mechanical energy of a simple harmonic oscillator. So, total or mechanical energy of a simple harmonic oscillator with a particle performing simple harmonic motion. That means the simple harmonic oscillator is addition of the kinetic energy plus potential energy is equal to the addition of kinetic energy and potential energy. Kinetic energy and potential energy. Therefore, mechanical energy is equal to kinetic energy plus potential energy is equal to K plus E. Substitute the value of equation 3 and 6, I think. Kinetic energy is half k square sin square omega t plus phi, and potential energy is half k square cos square omega t plus phi. From both terms there is common. Therefore, half k square into bracket sin square omega t plus phi plus cos square omega t plus phi. Now we know that in trigonometric sin square theta plus cos square theta is equal to 1. Therefore, only the half k square. Thus, the mechanical energy or the total energy is not depends on the position of a particle. So there is a main constant. There is a main constant. Thus, the mechanical energy that is equation by I think the 7. Thus, mechanical or total energy of a simple harmonic oscillator is not depends on position of a particle. Position of a particle and time. It is remain constant. It is remain constant. Here is now only we have to make the addition of the kinetic energy and potential energy to obtain the equation of the mechanical or the total energy. Total energy or the mechanical energy of a particle performing simple harmonic oscillator with a motion is equal to the addition of kinetic energy and potential energy. Therefore, E is equal to K plus P. That means the K plus E. Now we substitute the value of equation of kinetic energy and value of equation of potential energy. Half K square common. In bracket remaining is sin square omega t plus phi plus cos square omega t plus phi. Its value is 1. Because we know that the sin square theta plus cos square theta is equal to 1. Using this concept, E is equal to half k square. Here only the amplitude and constant is present. Amplitude is also constant. There is the maximum displacement. Therefore, mechanical or the total energy of a simple harmonic oscillator is not depends on the position of the particle and time. It is remain constant.